The title of my talk today is Fairness in Machine Learning, and I will cover aspects from political philosophy to data science algorithms. The topic will be much more focused towards unsupervised machine learning, and in fact, the data science part of it will be completely on unsupervised machine learning. So this was an ACM Cochin chapter talk. This is actually the re-recording of that talk. And that ACM Cochin chapter talk was held on the 6th of January 2020 at the Department of Computer Science in Cochin University. So starting off with a quick quote which attracted my attention from one of the papers, from one of the recent papers, not quite recent, it was Big Data and Society 2016. So algorithms are inescapably value-laden. Operational parameters are specified by developers and configured by users with desired outcomes in mind that privilege some values and interests over others. At the same time, operation within accepted parameters does not guarantee ethically acceptable behavior. So each and every step of the algorithm design is inescapably you're making some value or is aligned, those decisions are aligned towards certain values. So it is useful to think about the values that you embed into the algorithms that you design while you go about doing it. And that is especially true of data science algorithms, because you're already working with data that is generated by humans through various processes. So they might have a lot of biases and you might need to consider whether you would want to continue reflecting those biases in your algorithms, or would you want to have some correction for them. Okay. So the outline of this talk is split into two parts. One of the first part of it is basically on the political philosophy. I'm actually a student in political philosophy. I'm no way an expert in that area, but I thought it would be useful to cover a lot of these aspects which are very related, or which have a lot of significance while designing algorithms, while designing data science algorithms. So we look at motivation for fairness. We will look at popular notions of fairness. We look at fairness in the legal system, and so on and so forth. And then in part 2, we will look at fairness in clustering and fairness in retrieval, and in information retrieval, and similarity search and information retrieval in general. So first, before going into the political philosophy part of it, it is useful to think about why we need to be concerned about fairness in machine learning and data science. So data science has been becoming much more pervasive. So it is everywhere, and data scientists are increasingly working on data from varied contexts to address various problems. So basically, a data scientist, when you have a particular issue, and you have a lot of data, historical data, and then you would typically, typically a data scientist forms part of the mix these days, forms part of the team these days, because the data scientist would be able to analyze the data, interpret the data, and derive insights, and so on and so forth. So there are some dangers to having data scientists everywhere, because data scientists are not trained towards understanding social sciences in general, or human interactions and so on. So the nuances of those things are not something that forms part of the training for data scientists. So there are a lot of dangers. One is a data scientist might do some technical work without understanding the social context, and increasingly data science is being applied into aspects which matter to a lot of people's lives. So it becomes increasingly important to understand the social context, but data scientists don't necessarily have the training for that. And there is a thinking that I'm talking from a data scientist perspective, we are more rigorous than social scientists. There is a thinking that we are more rigorous than social scientists, and that social sciences, the way they do it is quite old-fashioned. We are doing it in a much more better and much more rigorous way, and so on and so forth. So that is not true, but that is a myth that a lot of data scientists, that is a thinking that a lot of data scientists have. And also, data science is a very mathematical profession. right? So you might be oriented towards a math part of it, and there is a possibility that people might justify an approach by the math that it entails. So if there is beautiful math in that approach, you generally have a predisposition to like it, which need not necessarily be a good thing. So ML based decision making, machine learning based decision making is everywhere, as I said, right? So machine learning algorithms make decisions that affect individual users and shape their opinions and choices in a variety of scenarios. There are a lot of examples. I'll talk about a few of them. One is automated CV screening and hiring. So recently, I came across a talk on machine learning usage in hiring, and there was actually a job scenario where you can apply to that job by including a 30-second video of yourself describing how you're suitable for the job. In fact, recently we hired a PhD student using such an application process. The PhD student, the candidate for the PhD studentship, was required to upload a video. And in this case, we actually went through the video ourselves, but in certain cases, it is not possible to go through each one of the applicant yourself. Especially in cases in India, for example, when the Indian Railways announces maybe tens of thousands of vacancies, you get tens of lakhs of applications, hundreds of thousands of applications. So it is not easy to sift through each of these applications on an individual basis. So you would need to do some machine learning based screening. And when you do this machine learning based screening, it opens up a lot of possibilities. For example, if you're using machine learning algorithms to go through a lot of these videos, then maybe well, you never know what kind of features the machine learning algorithm uses. Maybe it uses some of these features which are not so relevant. Maybe if somebody is in a casual attire and in a park and recording that video, there might be a bias for the machine learning algorithm against it, because it's a very minority kind of it's a very unusual kind of video, and given that you don't have enough historical data to support those videos positively, you might be biased towards rejecting them. So automated CV screening is a very important use case for ML based decision making. And in fact, even if you don't go through any of these processes, you are implicitly being influenced by machine learning algorithms all the time. Because when you're doing personalized ranking, and that is something that everybody does these days. For example, Google does it. So if you go and search on Google for something, it might show certain things that you might prefer to show you certain things higher up based on what you've searched before. And even Facebook does a lot of this personalization. Personalization in general has a lot of political implications, because personalization is essential, or the motivation for personalization is to improve click-through rates, for example, right? So the websites such as Facebook and Google want to make sure that they show things that are more relevant to you. And what is relevant to you is assessed based on your historical behavior, right? So they have a tendency, incentivized by these market factors, which require them to, which influence them to make these algorithms show content that you might click on, so that you might like their site better, or you might stay more, you might stay for longer time on their website, and so on. So essentially, they are trying to exploit the knowledge of your preferences based on your historical data. So if in a case of extreme personalization, what you're seeing is you're getting some kind of an echo chamber effect. You tend to see more and more of what you like, and in general, by seeing more and more of what you like, you tend to believe that is true as well. So personalized ranking is something that machine learning algorithms are used for very abundantly, and that can have some implications with respect to political implications in that sense. And YouTube autoplays the next video based on user interest, and that's also a case of personalization, right? So fairness is an important concern for data science because personalization might sway you towards a certain towards certain particular attributes or features, and that may not necessarily be a good thing because it disallows you from appreciating the wider diversity of the world, right? Or it, in a way, it undermines the multidimensionality of human life, and it undermines the exploratory instinct in humans in that sense. So let's look at fairness in law. Now, so why we care about fairness, and we should necessarily care about fairness due to some of these human factors. But we should also care about fairness because there is a legal regulation that requires you to care about fairness. And I'll talk about the Indian Constitution first. Article 15(1) of the Indian Constitution says that the state shall not discriminate against any citizen on grounds only of religion, race, caste, sex, place of birth, or any of them. I know it's slightly weird in terms of the phrasing, but I suppose that's a legal language that none of us are probably as used to. So the state shall not discriminate against any citizen on grounds of religion, race, caste, sex, place of birth, or any of them. And Article 14 actually goes a little further and says that the equality constructs should apply to any person. It's not just to any citizen. And these are days when we're talking about citizens and non-citizens much more than earlier. The state shall not deny to any person equality before the law. So every person, whether whatever be, gender, caste, citizenship, etc., should be is required to be treated equally as any other before the law. And when you go to the fairness constructs in the United States legal framework, there is something called the Title 7 of the Civil Rights Act of 1964. So it talks about fairness in advertising employment. Okay, so it relates a little bit to our automated CV screening kind of thing, but that's an automation thing. But here you're talking about even manual processes. So it says, it's a longish paragraph, but I'll just read the italicized part of it because it captures the, just italicized it based on, with an intent of summarizing it. It shall be an unlawful employment practice for an employer, labor organization, employment agency, etc., to print or publish or cause to be printed or published any notice or advertisement relating to employment, indicating any preference, limitation, specification, or discrimination based on race, color, religion, sex, or national origin, except that such a notice of advertisement may indicate a preference, limitation, specification, or discrimination based on religion, sex, or national origin when religion, sex, or national origin is a bona fide occupational qualification for employment. So when religion, sex, or national origin is a bona fide occupational qualification for employment, so when you're advertising for a post which requires people of a certain gender, certain religion, certain national origin, etc., then you can advertise it. But this bona fide occupational qualification for employment, sometimes abbreviated as BFOQs, is permitted only for sex, religion, national origin. It's not permitted for race. You cannot say that your job requires people of a particular ethnicity, for example whites, to be the only applicants, because that's not a bona fide occupational qualification. So the legal regulation prevents you from making such a job description. This is the United States law. Okay, and let's look at an example of unfairness. We talked about the US and Indian fairness constructs. Let's look at an example where we could violate one or both of them. So if a system screens candidates for whether they should take a pre-employment test, and the system requires only African American applicants to take a pre-employment assessment test, so it offers a more difficult route for African Americans to enter the job, because they're subjected to an additional hurdle which non-African Americans are not subjected to. So essentially you're giving them a more difficult route just because they are of a particular national origin or ethnicity. So that definitely violates the construct of fairness, because you're using race or ethnicity as an explicit construct to discriminate for whether for whether they have access to the easier route, or whether they should be subjected to the more difficult route for selection. So there could be, and that is a violation. So there could be other violations as well. For example, if a law offers people associated with a particular religion, regardless of what their origin is, but which country they come from, etc., if a law offers people associated with a particular religion a more difficult route for access to certain rights, and that could be, rights to live in a country, rights for citizenship, etc. So if a law offers people associated with a particular religion a more difficult route, by virtue of their membership in that religion, then that also violates the construct of fairness. That's an explicit and explicit violation of the construct of fairness that we discussed in the last couple of slides. So it should not be allowed. And what do you call this? If you have these kinds of instances of violation of fairness, then these kinds of instances are called disparate treatment. So you are treating people, you are denying parity of treatment to people based on their ethnicity or based on their religion. Okay, so that is what is called disparate treatment. So in formal terms, a sensitive attribute, it could be religion, it could be ethnicity, a sensitive attribute is considered in the decision making process directly to parameterize the decision making process. For example, a screening system that exempts non-African Americans from taking a test uses that sensitive attribute, which is ethnicity, in the decision making process very directly. So what do we do about it? How do we get rid of this unfairness? How about we just simply hide the sensitive attribute, right? Well, we could hide the sensitive attribute. And is it the case that if you simply hide the sensitive attribute, everything is fine? Okay. So it is not so, because there is another kind of disparate treatment which is called intentional. So earlier we talked about formal disparate treatment, which is when you use the sensitive attribute in a direct basis, and intentional is when an attempt is made to discriminate without direct reference to that sensitive attribute by using something else as a proxy, as a motivating factor, as a proxy. For example, if you use height as an attribute, okay, if you say that people above only if you set a height threshold and say the people above this height are allowed to apply, then just because of the correlation between height and gender attributes, you are automatically giving a more difficult route for women, because because males are correlated probably with higher height. So if you set a threshold and say that only people above this height may apply, then you're automatically preferring males. So in that sense, you are not using the gender attribute, which is the sensitive attribute, in an explicit fashion, but you are using it in an implicit fashion by using an attribute which in this case is height, that is very correlated with the sensitive attribute. Okay. So how do you eliminate? Well, you need to eliminate disparate treatment, right? So you would need to eliminate the usage of the sensitive attribute explicitly, as well as eliminate the usage of this sensitive attribute implicitly through some other proxy attributes. And what does elimination of disparate treatment seek to achieve? Okay, so if you eliminate disparate treatment, what do you achieve? You achieve something which can be called as procedural fairness. So you do not your procedure is fair. Your selection process is becoming fair, because you have not considered the sensitive attribute explicitly, nor have you considered any other attribute which is correlated with the sensitive attributes. So you are guaranteeing a sort of equality of opportunity. Okay, you're not explicitly denying them or implicitly denying opportunity to people who take certain people who belong to certain sensitive attribute categories. So you essentially are giving them a level playing field, and you ensure that similar individuals get similar outcomes. These are all the same things, and you can think about these are all different perspectives of looking at it. Your procedure is fair. So essentially, you mean to say that you're giving equality of opportunity. Everybody has the same difficulty, is subjected to the process which has the same amount of difficulty, and you're giving them a level playing field. That's equality of opportunity, and which means that if two people are similar to each other, and this is more talking from a data science perspective, when you can assess similarity kind of automatically. If two people are similar to each other, if two people get a similar kind of profile of exam marks in a selection process, you get they tend to get the same outcome, whether it be a selection or a non-selection. So equality of opportunity is decision making which treats people similarly on the basis of relevant features given their current degree of similarity. So similarity is a very key construct here, because when you take two people, you assess them based on the similarity, and if they are very similar, they get similar outcomes. So similarity is not just simply assessing people, but you are assessing their performance in tests, or you're assessing, in certain cases, depends on changes from scenario to scenario. So you're creating what is called a meritocracy, which says that desirable jobs or positions should be offered to the best qualified applicants through competitions that no one is excluded from entering. Okay, you're not explicitly excluding or implicitly excluding by means of some proxy attributes. And this is something that resonates with some political leaders as well. For example, Margaret Thatcher in 1975 famously said, or it has been quoted in many places, that our party is the party of equality of opportunity. And as you know, Margaret Thatcher has been criticized for her right-wing policies quite extensively. And you find, and if you find yourself agreeing with the equality of opportunity construct that Margaret Thatcher is so much in favor of, maybe you should start wondering whether you're missing something. Okay, and let's look at the issues with equality of opportunity, and then we'll get to what we are missing if we simply what we would be missing if we guarantee if we simply resort to guaranteeing equality of opportunity, or we're asking the question, if we guarantee equality of opportunity, is everything going to be fair thereon? Okay, so there is an unfairness objection, and this largely comes from John Rawls, a political philosopher who wrote a famous book called A Theory of Justice. The unfairness objection says that in societies with significant social inequalities, people start out with unequal opportunities to acquire qualifications, right? So there are significant inequalities in societies, and especially in developing countries, the inequalities are very large, right? So in such societies, if you provide equality of opportunity, then and reward people based on their qualifications, because these qualifications are parameterized by the social inequalities, you are primed to get better qualifications, or you are socially primed to get better qualifications if you're born in a more affluent neighborhood, or in a more affluent or in a favorable caste, etc. Then your outcome is parameterized by your qualifications, and your qualifications are determined by your position in the social inequality, in the social spectrum, right? So meritocracy tends to reflect the social inequalities. So if you simply use meritocracy as a selection criterion, then your social inequalities will be reflected in the outcome of that selection process as well. Okay. So let's look at two cartoons just to illustrate the idea, right? So there could be people who are genetically disadvantaged, or it could also be due to malnutrition, etc. They don't attain the normal, what is considered as a normal adult height, right? So let's consider these three people. Who one of them is attains a usual or expected adult height. Another one is a medium person. And the third one is a short person. So if you provide them equality of opportunity, it is equivalent to giving them the same platform to try and achieve something. In this case, you're trying to achieve they're trying to achieve a view of the baseball match, right? So if you provide them the equality of opportunity, your outcomes are primed, your outcomes are determined or are skewed towards people who are socially advantaged. So here, the person who has attained adult height, normal adult height, I wouldn't say normal, but essentially adult height as expected, can see the baseball match, whereas somebody who is extremely short cannot see it, right? And this is due to maybe congenital, or this is due to genetic or other malnourishment kind of factors, but there could also be other factors which you cannot really do anything about. For example, the social inequalities that exist along the gender spectrum, right? So you could, women or particular genders are expected or stereotyped in order to do certain things. So there is a huge inequality in the gender spectrum, right? So if you give everybody the same difficulty of the route, so essentially you're giving them a 100-meter race, but well, the 100-meter race could be to attain a level of technical proficiency in your job, etc., etc. But a particular gender needs to do a lot more things along the way, whereas the other gender, being socially advantaged, does not need to do so, right? So your outcomes will be skewed towards the more favored gender, to the more advantaged gender, right? So this is the problem with the equality of opportunity. You can say you can provide equality of opportunity, but that is about turning a blind eye to the inequalities, to the social inequalities that exist in society. So even when disparate treatment is avoided, even when you don't make use of the gender attribute or don't make use of proxies such as the height attribute, etc., an advantaged group may receive a much higher rate of favorable decisions than a disadvantaged group. And this is not something very surprising, because if you profile people who have reached a particular level of attainment, who have reached a particular level of achievement in the professional circles, especially in the private kind of job market, where there is no reservation, etc., you can see that it is so highly skewed in favor of the forward caste, so to speak, right? So that has the corporate environment, I wouldn't say it has procedural fairness, but even if it had extreme procedural fairness and equality of opportunity, forward caste might see a much higher success rate than backward caste, Dalits and whatever it is, right? So there could be a lot of unfairness, even in the impact, even when you take disparate treatment out of the equation. So disparate impact. Let's look at disparate impact. That is the second criteria that we talk about. So a system administers a job test and commits to hiring based on the results of this test. And this would result in a low pass rate for African Americans, because African Americans have been traditionally disadvantaged, and we're talking about the US context here, right? So you would see a much lower pass rate for African Americans. And it's important to say that, if we take the far right argument out of the equation here, the far right argument could be that certain sections of society are maybe inherently more privileged than others, are inherently smarter than others, and so on. So we hear such things quite a lot, even within the India context. We say that there are things that say that people of certain castes are very intelligent, etc. So we're taking that thing out of the equation. We believe that, I assume that we're saying that we do not agree to that. Okay, while we say everybody is born equal, okay, and with equal capabilities, if you agree to that argument, and which is an argument that everybody should agree to, or would agree to, and if you agree to that argument, then the difference in outcome is a result of the difference in social inequalities, right? It's a result in the differences that accumulate. They are equal at birth. The differences start accumulating from day one and all the way until the age of 20 or 25 whenever they apply for jobs, etc. Okay. So that is called disparate impact. And let's see whether the legal system has any kind of safeguards against disparate impact. So if you look at the law in the US, there is something called the Uniform Guidelines on Employee Selection Procedures, which was in 1978. It says that if a selection rate for any race, sex or ethnic group which is less than 4/5 of the rate for the group with the highest rate will generally be regarded by the federal enforcement agencies as evidence of adverse impact, while a greater than 4/5 rate will generally not be regarded by the federal enforcement agencies as evidence of adverse impact. So let's take the case of a gender group. Okay, so if males if females have less than 80% success rate as that of males, okay, so if males have a success rate of particular thing, and if the female success rate for jobs and for employee selection in a particular organization happens to be less than 80% of the male success rate, that is a 4/5, then the onus, the burden of proof shifts to the employer. So well, in the case of general jurisprudence, the burden of proof lies on the person who is criticizing, right? So here you have set an objective criteria. We're saying that if the female success rate is less than 80% of the male success rate, or this can apply across any kind of group, it need not be just gender group, then the onus, then the burden of showing that your selection process is all right shifts to the employer. Okay, so one can sue an employer if there is evidence of adverse impact. So if you have evidence that the success rate for females is less than 80% of the success rate for males, then you can sue the employer, and the burden of proof shifts to the employer. So the default position becomes that the employer is using a discriminatory process, and the employer needs to justify why that process is not discriminatory, etc. And the law in India is quite unique in this regard, because there is an affirmative action program which is built into the Indian Constitution, which is called the reservation system, and it is probably the only quota-based system, but it applies only to state institutions. It applies only to government jobs. And Article 15(4) is what makes the provision for it. It says that nothing in Article 15, which talks about equality, or in Clause 2 of Article 29 shall prevent the state from making any special provision for the advancement of any socially and educationally backward classes of citizens, or for the scheduled caste and the scheduled tribes. And I consciously avoided talking about that economically word there, because that was a recent inclusion in 2019 by the government. So currently it is socially, educationally and economically backward classes of citizens, but earlier it was just socially and educationally backward classes of citizens, or for the scheduled caste and the scheduled tribes. And Article 46 says that the state shall promote with special care the educational and economic interests of the weaker sections of the people, and in particular of the scheduled caste and scheduled tribes, and shall protect them from social injustice and all forms of exploitation. So the reservation system says that the representation of particular categories should be at least this much, right? Should be not at least, yeah. Well, basically it's saying it's at least, but a lot of cases you don't fill up the quota. You are unable to fill up the quota for like CSTs, etc., and so on and so forth. So you end up not having that. But the law requires you to provide at least this many, well, at least a particular fraction of jobs to particular categories, and that directly addresses the impact question, right? So you're looking at the selection process. You can one way is to take the selection process and take out some and modify the selection process in such a way that the impact is fair across all groups, or the other way is to just use these quotas and say that you have set that the impact should be fair. Now, having said that the impact should be fair, impact as in like the amount of government posts being occupied by various groups and so on. So that is already set. Now you kind of fill up the posts, right? You can have your selection process. So you don't need to worry about that aspect in your selection process. You're just required to take these many people of this many of particular categories, and it may soon be the case that you will see this quota-based system. Spreading out into other kinds of other geographies as well. For example, EU is to push for 40% quota for women in company boards. So let's look at elimination of disparate impact, right? So we talked about disparate impact. Let's look at elimination of disparate impact. So we saw this case where we had equality of opportunity. So that is about disparate treatment. So we have avoided disparate treatment. So if you consider height as a sensitive attribute, and you have three categories, high, medium, and low, and you have 33% representation of each of these categories in the population, right? And if you use this process of selection if you use this process, everybody wants to see baseball, and if you use this process of selection as to who would see baseball, then what you get is a disparate impact. You get 50% among the people who can see baseball, 50% are of high height, 50% are of medium height. Okay, so that is a disparate impact. So we are starting to talk about these vectors, right? And you can compare vectors. So we are talking about mathematical operations. We'll come back to this when we discuss the data science aspects of the talk, data science aspects in the talk. But essentially, if you want to eliminate disparate impact, you set up a different configuration, which would look like this. And with this, you are being able to eliminate disparate impact because the fraction of people who can watch baseball along this height attribute is exactly the same as the representation in the population. So essentially everybody can watch baseball, right? So you can eliminate disparate impact in this way. So representational distribution is preserved along the sensitive attribute. So that's what you have done by this rearrangement, right? You have given these two platforms to the person who is underprivileged from the height attribute, just so that he can also watch baseball, right? And by doing that, you're able to guarantee that you're able to ensure that the distribution of people who can watch baseball along the height attribute is similar to the distribution of people in the population as well. Okay. So what does elimination of disparate impact seek to achieve? We asked the same question in the case of disparate treatment, right? So here we are asking, what does elimination of disparate impact seek to achieve? So the elimination of disparate impact seeks to achieve what is called as distributive justice, and you are trying to minimize the inequality of outcome. You are trying to minimize the inequality of impact. And in a way, in a light way, you're trying to maintain the representational balance in outcome across the sensitive attribute groups. So here, the notion of sensitive attributes and groups is quite central. So when you talk about disparate impact, you are already implicitly talking about sensitive attributes and groups. And in this case, you could treat seemingly dissimilar people similarly, on the belief that the current dissimilarity is a result of injustice. So you could have two people who get similar, who get very dissimilar marks, but they might both get selected for the job if the current dissimilarity is judged to be the result of injustice that has accumulated along the course of their lives so far, the social injustice. So you're trying to kind of remedy the social injustice that is accumulated by creating a system that will treat seemingly dissimilar people similarly, give similar outcomes to people regardless of their performance being very dissimilar, and by that mechanism you are trying to achieve what is called as distributive justice or minimized inequality of outcome. So let's just line up these two notions here. So the first one is about eliminating disparate treatment. You provide equality of opportunity, you get procedural fairness, you give a level playing field, but even if you do all these things, you could still have the social inequalities reflect in your outcomes. So by eliminating disparate impact, you're trying to equate the outcome across groups, and you're trying to get some representational balance or distributive justice, and dissimilar people may be treated similarly to ensure outcome balance. Okay. So the relationship between the two notions on a political axis, I'll just briefly go through this slide. The right frequently distinguishes itself from the left by arguing that the left favors equality of outcome, whereas the right favors equality of opportunity. So the left generally says that the social injustices should not reflect in the outcomes. So the left argues for equality of outcome, whereas the right favors equality of opportunity. So that's why Margaret Thatcher's position was very much towards equality of opportunity. Her party was definitely regarded as very right wing. So if you spread opportunity more broadly, you tend to get more equal outcomes than if you clump up opportunity more narrowly. So if you have less social injustice, you don't need to have that correction for equality of outcome much. Because if you have less social injustice, you can never get rid of social injustice completely, because there are this would exist to some extent or the other. But if you have less social injustice, then even by simply using equality of opportunity, you might get equality of impact. Right? If you have absolutely no social injustice, equality of opportunity implies equality of impact. So equality of outcomes versus opportunity. There is this interesting chart which plots countries based on their equality of opportunity and equality of outcomes. So here, as you can see, Norway has a high equality of outcome and also has a high equality of opportunity as well. Right. So if you have a high, if you have less social inequalities, then by simply giving equality of opportunity, you can guarantee equality of outcomes across the sensitive attribute groups. So there is this notion called luck egalitarianism, which says that outcomes are of two types. One is outcomes due to good or bad luck. For example, you might be just prone to some diseases because of your genetic makeup, or you might be living in an area where a natural disaster struck, so your outcomes are of less quality because you're unable to achieve so much because you're suffering due to natural disaster. And outcomes, some other outcomes can be attributed to conscious choices, such as career choice. For example, if you have a bunch of choices before you, you might be consciously choosing a particular career path. And if outcomes are, some outcomes can be attributed to such conscious choices, right? So the luck egalitarianism philosophy says that the overall inequality of outcomes, so it doesn't say that the overall inequality of outcomes should be reduced. It says that the overall inequality of outcomes should be completely determined by the conscious choices. So the overall inequality of outcomes should not be dependent on the outcomes due to luck, such as genetic makeup, natural disaster, etc. One might argue that career choice is not so much of a conscious choice because your career choices are sometimes very highly influenced by the market, especially over the last maybe 3 to 4 decades in Kerala and broadly maybe in India. There's been a huge shift towards professional degrees and so on. So you might be making a career choice. Based on the available choices, and this available choices, or at least the perception of available choices, is potentially only professional degrees. So your career choice is hugely determined by certain other factors already, because certain other factors have already taken out some of those choices. So career choice need not be necessarily considered as a perfectly conscious choice. That's what I'm meaning to say. So the boundaries between luck and conscious attributes, or luck attributes and conscious attributes, need not be very crisp and clear. It could be very blurred as well. So the intuition of luck egalitarianism is that the overall inequality of outcomes makes some people worse off, and it is fine for some people to be worse off than others, as long as the disparity is completely attributed to conscious choices, as against their luck attributes, such as genetic makeup and natural disaster, which is something that they have no hand in deciding. So it's a bad thing for some people to be worse off than others through no fault of their own. And it doesn't stop there. Amartya Sen talks about something called equality of autonomy. So he says that the ability and means to choose our life course, sometimes you can even call that as capability. The ability and means to choose our life course should be spread as equally as possible towards across the society. And he says that the equality in the degree of empowerment, people have to make decisions affecting their lives, how much choice and control they have given their circumstances, right? So you're trying to empower people into making these choices. So well, just to give a bad example, well, I'm not sure whether it's an appropriate example. Let's say an autocratic regime is in place and you have a huge population, and they say that there are 10 jobs. Let's hypothetically assume that there are only 10 jobs, and they say that 1/10 of these people, so when you are born, you toss a coin. The government tosses a coin and says that okay, based on this coin toss, you have decided that you go to career choice 1, and another person goes to career choice 2, etc. So eventually you get impact parity, right? So regardless of what conditions you are born in, you have a 1 in 10th chance of going into a particular career, and eventually the proportion of people across careers is not is quite uniform. But that is something that is imposed upon you. You did not have the choice. You were told from the time of birth, or from the time when you can comprehend things, that this is the career choice that has been decided for you. So that is not quite a nice thing, because they had absolutely zero ability to choose their life course, and still the outcome is all right. So you have you have satisfied the disparate outcome, the elimination of disparate impact, but you have not done something meaningful because you have not given the choice to people. So essentially, equality of autonomy is in a way trying to say that the ability and means to choose our life course should be spread as equal as possible towards a society. So you're kind of disallowing the situation where you can achieve parity in impact by an autocratic regime that pushes certain decisions down the throat of individuals. Okay. So in summary, disparate treatment and disparate impact are two different notions of fairness. Disparate treatment is about equality of opportunity, whereas disparate impact is about equality of outcomes across groups. And there are quite a lot of conflicts between these two fairness doctrines. So it's not a fairness is not quite a solved problem. As we said, we can ask the equality. We can ask about the equality of what. You can go further. You can go. There are many layers that you can peel off and see, and have more nuanced positions, etc., etc. So let's look at fairness in clustering and retrieval. Right. So first, we'll start off with fairness in clustering. So what is clustering? Clustering is a machine learning task that groups objects into clusters of similar objects. Okay. So let us say that you are maybe the Indian Railways, and you have announced some maybe 10,000 vacancies, and you've gotten some 10 lakh applications or 1 million applications, right? So what do? You cannot go through each one of these applications separately. So what you might do, if you had at your disposal a machine learning system that does clustering, would be to take these things and make them into clusters. So you kind of make maybe let's say 1 lakh clusters, right? 100,000 clusters. And once you have that 100,000 clusters, so each cluster might have like say 10 applications, and then you take a representative application from that cluster and you see whether that application satisfies your criteria. And your assumption is that the cluster being all those 10 applications being in the same cluster is an indication that all of them have something similar to each other. So you take that representative application and say and assess its suitability to the job. And if it is suitable to the job, then you shortlist all the 10 applications in that cluster. So that's how you are achieving some amount of savings in the manual effort that you put in, right? So achieving savings in the manual effort by means of doing this clustering and treating all objects in that cluster as essentially indistinguishable from each other. You take a representative, make a decision based on that representative and apply it to the entire cluster. Okay. So if you have a set of objects like this, and in this you are making the assumption that if two objects are close to each other in this space, so this is a two-dimensional Euclidean space, if two objects are close to each other in this space, then they are more similar to each other, then they're quite similar to each other. Okay, so if you want to build a clustering over this data objects, what you might do is you start off with you might essentially create 3 clusters, and the blue cluster is a set of applications on the bottom left. The red cluster is a set of objects in the middle, and the purple cluster is a set of objects on the right hand side. Okay, and you could have a representative for each of these clusters, and the representative could be the midpoint of that cluster, could be the centroid of that cluster, right? So you take all these red objects and take their average, and that average is represented by means of this square in red. So the typical quality measure of clustering would be, well, how would you say what is a good clustering? How would you say whether this clustering of groups of objects into these 3 clusters is a good clustering? So a typical quality measure of clustering would be the sum of distances of each object to its cluster centroid. So you take each one of these objects. So if it's a blue object, you calculate the distance of that blue object to the blue centroid. And if it's a red object, you calculate the distance of that red object to the red centroid. And you add up these distances across all the data objects, right? And you get a value. And that should be minimized. And you need to learn a cluster. You essentially need to estimate a clustering in such a way that these clusters are tight, right? So all these cluster objects are very close to the centroid. So that's what you look for as a typical quality measure for clustering. And let's look at profiling clustering as a task on the basis of fairness, right? So we saw 2 notions of fairness. Let's try and see how clustering task could adhere or not adhere to certain notions of fairness. Okay, so common clustering formulations try to minimize the distances between objects in the same cluster. They try to put objects into clusters in such a way that the distances between objects in the same cluster is minimized and the distances between objects across cluster is maximized. So if 2 objects are in the same cluster, they should be very close to each other, right? And vice versa as well. So if 2 objects are very proximal, they would likely get assigned to the same cluster. So that's what they try to achieve. So you might recollect that we said similar individuals get similar outcomes is a notion that is aligned with the elimination of disparate treatment, or that is aligned with the equality of opportunity paradigm. So if 2 objects, so what clustering does is simply to put objects that are similar to each other into the same cluster. And if you consider cluster membership as an outcome, then this is essentially very much aligned to the notion of equality of opportunity or the elimination of disparate treatment. So there is no mechanism within the high level clustering objective to avoid disparate impact. So we've considered disparate treatment by simply creating this nudging these clustering formulations to minimize distances between objects in the same cluster and maximize distances between objects along other cross clusters. By doing that, you are already trying to be, or you're already very well aligned with the equality of opportunity paradigm, but you do not have any mechanism within the clustering objective in order to avoid disparate impact. Okay, so there could be three ways of doing this, right? One is to pre-process the input. And we're getting into slightly more technical terms here. One is to pre-process the data set in such a way that any clustering over the pre-processed data set will provide fair clusters. We'll look at some example there. Okay, and the other one is to modify the clustering method and to create a new formulation of a clustering method which will provide fairer clusters. The third one is to use any kind of clustering method and then perturb the clusters that you get, kind of change the clusters that you have already produced by simply using a cluster, by simply using a clustering, and post-process the result in order to correct for fairness. We will look at an example of the first two. One is a NIPS 2017 paper, and the second one is a paper in which I was involved in, which will be published in EDBT 2020. Okay, so fair clustering through fairlets. So this is a NIPS 2017 paper. So this is about clustering under the disparate impact doctrine. So you're trying to achieve a trade-off between disparate impact and disparate treatment. Disparate treatment, as I said, is already achieved in the traditional clustering formulation, the clustering formulation that tries to minimize the distances between objects in the same cluster and maximize the distances between objects across cluster, already aligns very well to the disparate treatment paradigm. Now, or elimination of disparate treatment paradigm. So here we are trying to use the disparate impact doctrine. Let's say that there is only one binary sensitive attribute and there are two values x and y. The objective is to ensure that the x and y groups should have approximately proportional representation within each cluster and the output, right? So let's say that the x and y is gender, right? Male and female. So you are expecting that the gender ratio within each cluster should be similar to the gender ratio across the data set. Okay, so you want to pre-process the data set to create a fairlet data set, that's what they call it, followed by application of any clustering method. Okay, let's look at an example here. So let's consider that this is the set of x objects and this is the set of y objects, and you want to get a clustering, right? You want to cluster this data set. And I have just colored it based on the sensitive attribute because we are focusing on the sensitive attribute. And we'll look at how they achieve this, right? So you take one particular object and match it with an object of the other color. Okay, so you take this object, you take this green object and match it with an orange object. Okay, you take another pair comprising different colors. And you do this for every object. You pair up each male object with another female object, with a female object, right? And you do this for everybody. And now you have these edges, right? So what you can do is, what they try to do is to represent each of these pairs as a single object in this space. So what they do is estimate a single object in the space, which is this red object, which stands for that pair. So that is in the middle of in the midpoint of that line, and you can create these red objects in each of these lines, right? So you get a number of these red objects. Now you forget the fact that there were these pairs. Now you consider only these red objects. You remove those pair objects and you remove even these edges. Now you can cluster this object, right? And if you cluster, not this object, you can cluster this data set of red objects. And what is our primary intent in doing this clustering? The primary intent in doing this clustering and in ensuring some fairness in clustering is to ensure that every cluster has an equal proportion of x and y objects, right? Now each one of these red objects contains one x object and one y object, and you're forcing the clustering to operate on these red objects. So this clustering application or the clustering algorithm cannot split up a red object, because you have one representation for a red object. It cannot split up that red object. So if you do this clustering over this red data set, then what you get is you get clusters of objects, each one of which is a set of red objects, right? So let us say that you get a cluster which contains 3 red objects, and each one of these red objects contains 1 x and 1 y. So 3 red objects, if you split it up, you get it as 3x and 3y. So you can never achieve a cluster if you're clustering based on clustering just these red objects. You can never get a cluster which has a skew, which has an asymmetric representation between x and y, because each of these red objects is automatically bringing 1 x and 1 y with itself, right? So this is a simple way of achieving some amount of fairness in clustering. So we are talking so far about a balanced data set case. You can create a mapping between x and y objects to create balanced pair clusters, and you prefer to minimize the distance between the pairs that are matched. You treat these pairs as objects and cluster them, and any cluster will have a balance of 1, essentially that equal number of x objects and equal number of y objects, since you can only pick pair objects. Okay. So the question is, can we do a better matching? So what is a quality measure? What they try to achieve in this NIPS paper is to achieve this one in principle, but in addition also to get a good matching. All right. So here we're matching objects, matching each x object with a y object, right? So you're also trying to get a better matching. And what is meant by a better matching? So you get this thing. You have created this matching here, and you have another matching here on the right hand side. And which one would you consider as a better matching? You would generally consider the right hand side as a better matching, simply because the edges, the total length of the edges is much smaller in the right hand side. So objects are getting matched to objects. An x object is getting matched to a y object that is much closer to itself than in the case of the left hand side matching, right? So in a way, if you're looking at if you're taking 2 objects and taking the midpoint, let us say that you're taking 2 objects. One object is that one object has a mathematics score. Let's say that you're talking about exam scores, etc. One object has a math score of 10 and another object has a math score of 90. And you're representing it using the midpoint. So your midpoint is a mathematics score of 50. And that is neither representative of the 10 object and neither representative of the 90 object, because it's far enough from 10 and far enough from 90. So by creating that kind of a representative, you're not being truthful to the data, to the underlying data. Whereas if you take if you match objects which are very close to each other, for example, you match an object which has a math score of 85 with an object which has a math score of 90, then your midpoint is 87.5. That is quite reflective of both of these, right? So you would generally tend to prefer to match objects with those that are closer to each other. So in that sense, the right hand side matching is better, and that's what they seek to achieve in the NIPS in the NIPS paper. It is then NIPS, and the conference has been renamed as NIPS. So I mean, you can refer to it as NIPS as well. So let's look at the second paper, which is about modifying the clustering method so that the clustering produces equitable impact across groups defined on sensitive attributes. So in the earlier method, as we saw, you can only look at attributes. You need to match objects, right? And if you need to match objects and match x and y objects, then the sensitive attribute, in this case it could be gender, male and female, needs to be a binary attribute. Whereas there could be other sensitive attributes which are non-binary. For example, you might not want to, you may want to eliminate discrimination based on race or ethnicity. And in that case, it is a non-binary attributes because there are so many ethnicities. And you might also want to eliminate disparity based on, let's say, age. So I remember there was an article which so a big multinational company was apparently laying off a lot of people in the United States, and there was a trade union which tried to analyze these layoffs and found that the company was potentially using an age-based policy for layoffs. The company was laying off people of higher age because potentially they were more expensive to maintain because they earn higher salaries and so on. So there was a discrimination. There was an allegation of discrimination based on age against that multinational company at that time. Right? So you might not want to discriminate based on age as well. Age is not even a categorical attribute. Ethnicity is a categorical attribute in the sense it has 4 or 5 different ethnicities and each object belongs to one of those ethnicities. But this is a numeric attribute, right? A person could have an age which is a number. So you might want to eliminate disparity, or you might want to eliminate a disparate impact on non-binary attributes as well. So our method can handle any number of sensitive attributes, and it targets to both maximize the cluster quality over the non-sensitive attribute. So if you take out the non-sensitive attributes, if you take out the sensitive attributes, let's say you are doing a job shortlisting, and you take out the non-sensitive attributes, which is maybe age, gender, ethnicity, etc., and you want to maintain a clustering quality over those non-sensitive attribute, and also maintain equitable representation over the sensitive attribute. So if the entire population has maybe 10% of people with their age in their 30s, you might also want each cluster to have 10% of people in their 30s. Right? So the equitable representation objective, I won't go into the math of it that much, but I'll just outline what we're trying to achieve here. Right, so we will outline it based on this little cartoon itself. So if height, one of medium, high, and low, is a sensitive attributes, its data set representation is 0.33, 0.33, 0.33. Right, so you have only 3 people in this toy data set. So let us treat those who can see baseball as one cluster, and those who cannot see baseball as another cluster. So there are 2 clusters. Those who can see baseball and those who cannot see baseball. And among those who can see, you have a representation on this attribute which is 0.5, 0.50. And among those who cannot see, there is only one person, which is the low height person. So you have 0, 0, 1. Okay. So the inequality of this clustering. So this clustering is essentially 2 clusters. One is those who can see baseball, another one is those who cannot see baseball. The inequality of representation of this clustering could be considered as a sum of 2 factors. One is the difference between the data set proportions on the height attribute and the cluster 1 proportions on the height attribute. So that is the distance between this vector 0.33, 0.33, 0.33 and 0.5, 0.50 plus the distance between the representation in the data set and the representation in the second cluster. Okay, so this gives you a notion of inequality of representation, right? And this is only for the height attribute, and you can do the same thing for other attributes as well, for age, for gender, for ethnicity, for various attributes that you might want to guarantee equality over. So in a way, our equitable representation objective uses this construct, but generalizes this construct or enumerates this construct over all sensitive attributes. So you first set objective equal to 0, and for each sensitive attribute, for each cluster, you measure the representation in that cluster for that sensitive attribute, and you compute the distance between the representation in that cluster for that sensitive attribute and for the entire data set over that sensitive attribute. You compute the distance between these representation vectors and you add it to the objective. So the objective quantifies the overall distributional inequality across all clusters, across all sensitive attributes. And our method simply attempts to minimize this. Actually, there's a little bit of a variation here because we wanted to ensure some amount of balance in the clusters and so on, but I'm not getting to those mathematical details. Our method attempts to minimize this objective in tandem with the clustering objective. Okay, so you're trying to minimize the clustering objective, which is basically the distance, basically the total distance for every object and its centroid, and also trying to minimize this distributional inequality objective. So this helps achieve a trade-off between clustering objective and equitable impact across sensitive attribute groups. Okay. So there have been a number of works on clustering, on clustering fairness. For example, there's a paper called Scalable Fair Clustering, Privacy Preserving Clustering with Constraints, Guarantees for Spectral Constraint with Fairness Constraints, Fair Algorithms for Clustering, Fair Course and Streaming Algorithms for Fair K-means Clustering, and so on and so forth. So there are plenty of algorithms, plenty of techniques, and it's a very thriving research area. But I've just introduced two methods, and I think I'll stop there for clustering, and we will go quickly into fairness in retrieval. Okay. So similar to what we did earlier, let's look at retrieval as a task, and let us try and analyze it or profile it against these two notions of fairness that we looked at. One is disparate treatment, and the other one is disparate impact. So what do common retrieval formulations try to do? So what is a retrieval system? Let us say that you watched a movie and you liked it so much. So what you would do is you would go to maybe a movie search site, like say IMDb or something, and you might do a movie search engine and then try and find similar movies to that movie, right? Because you like that movie so much, so you might like similar movies as well. So common retrieval formulations try to ensure that the results are scored in relevance to the query words, in accordance to the relevance to the query. So in this case, you're querying with a movie, and you are trying to rank each one of those movies in your database in terms of relevance to the queried movie. Okay. There is no explicit usage of similar objects to be scored similarly. So you're measuring the relevance of each movie, measuring the similarity of each movie to your movie. So let's say that you watched a movie like, let's say, X. Okay, you have another movie Y, and you measure its similarity, and let's say its similarity is quantified at 0.95, and you have another movie Z, and you measure its similarity, and let's say your measured similarity is 0.9. Okay, so so Y would come first in the list and Z would come second. Okay, so there is no explicit usage of similarity between Y and Z. But there was a paper called the Cluster Hypothesis in Information Retrieval from Van Ritsbergen, who was a professor in the University of Glasgow, and this was in 1979. He said that even though you do not make use of similarity between Y and Z, okay, similar documents or similar objects tend to be relevant to the same request. So if there is an object, if Y is relevant to a particular query, it tends to so happen that Z is also relevant to that query, as long as Y and Z are very similar to each other. So this was more of an observation at the time. This is not something that that is explicitly taken care of, but this is more of an observation as to how IR systems work. So, but later on, this has been used in IR systems more explicitly. So you do some kind of clustering and then search only within that cluster. So let's say that you're looking for movies, and you're searching for a movie with a comedy genre, and you only search for movies with a comedy genre, or you only search for movies within the same cluster. Your retrieval system might only be doing that, because it just assumes that there is a very low likelihood that that anything outside this cluster would be relevant to your query. Okay, so this has been used in IR systems very explicitly. So closely associated documents tend to be relevant to the same requests. So that means that, what is this, right? Similar objects tend to be relevant to the same request, or similar objects tend to be brought up in the same for the same queries. So essentially, you're saying that similar objects might get similar outcomes. So similar to our observation with respect to clustering, there is no mechanism within typical retrieval engines to cater to avoid disparate impact. So disparate treatment is already taken care of, because as you can see here, similar objects tend to be relevant to the same request, so similar objects tend to be brought up in for the same queries, and they get similar outcomes. Outcome is whether you are brought up in a query or not. So they tend to be relevant to the same query, they tend to be brought up in the same queries, and so on and so forth. So there was this paper called Ranking with Fairness Constraints, which is retrieval under the disparate impact doctrine. Okay, much like clustering, right? So there is no mechanism within retrieval to address this disparate impact, to address the elimination of disparate impact. So you need to build fair ranking algorithms, much like you had to build fair clustering algorithms, because even in that case there was no disparate impact addressing. So the setting here is that there are possibly overlapping groups in the data, denoting sensitive groupings. Okay, and the objective is to ensure that the representation of different groups are within this group specific lower and upper bounds. So in a way, you are saying that, let's say that there are 50% males and 50% females. You're trying to ensure that if you're searching for similar people using a queried person, your rank list also contains, your top 10 rank list also contains 5 males and 5 females. Okay. So an optimization formulation has been devised to determine a ranking with constraints on fair representations. Okay. So I'm not going to the details of it, but I'll have one slide quickly talking about some details, but not too much about it. Okay. Let us say that Wij denotes the value of putting an item I at position j in the retrieval result. Okay. And Aij denotes a binary choice of whether item I was chosen to be put at j in the retrieval result. So your optimization for the best relevant result is to whenever Wij is high, you want to set Aij to 1. Right? In another way, you might be able to figure this out yourself, that in another way you're trying to get a ranking, get an assignment on A vectors of A vectors in such a way that you want to maximize setting Aij to 1 when Wij is high. So mathematically it's just about optimizing this objective function. Okay. And this does not consider fairness, right? And for fairness, you want to put some constraints, and that constraint could be you want to have at least 30%. You want to have at least 30% representation of females, at least 40%, at least at most 50% representation of females, and similarly for males, at least 30% representation of males, at most 50% representation of males, etc. So so you impose a constraint saying that you want to maximize this objective, and that is to bring up the best result to the user. But in addition, you need to satisfy this constraint, which says that you need to be satisfying this lower and upper bounds. Okay. So there has been other work on disparate impact as well. So there was a paper in CIKM 2017, which is about a fair top K ranking algorithm, and there is a paper on designing fair ranking schemes in SIGMOD 2019. So what I would like to now look at as a last slide is to talk about something interesting in retrieval, and this is the attention relevance disparity in retrieval. So let us say that you have these objects. So you're querying with a movie, right? Let's say O, and you're computing the relevance of each of the movies in your data set with respect to this queried movie. So O1 has a relevance of 0.97, O9 has a relevance of 0.84, and these are the movies in your database. Your database has only 5 movies. And what would you do if you were a retrieval engine? You would put the top ranked thing, most relevant thing, at the top position. So you put O1 at the top position in your ranking result, and you put the second most relevant one, which is in this case is O5, as a second result. And similarly, O3 figures third, and O9 figures fourth, and O6 figures the fifth. Okay. So consider you are searching on Google, right? And you have 10 results before you. You tend to mostly spend a lot of time on the first result, spend much less time on the second result, spend much less time on the third result, and so on and so forth. By the time you are reaching the 9th result, you are most likely not to even notice it. So in a way, the decay of attention is rapid as you go down. So here the decay of scores, the decay of relevance scores is slow because you're ranking them linearly on the basis of scores. But your attention decay is very fast. Just because O1 has gotten 2% more score, more relevance than O5, doesn't mean that it gets only 2% more attention. It gets much more attention. Gets probably twice as much attention, or maybe not twice, whatever it is. It gets much more attention. So the ordering, the relevance decay is linear and slow, whereas the attention decay is fast, just because of human factors. And it is infeasible to ensure that O5, the relevance, the attention that O5 gets is only 2% less than the relevance of O1, less than the attention that O1 gets, because it's impossible to ensure that your attention is at par with the relevance scoring. And that is because that is simply because of the nature of it, right? Because you have only these positions to put in. You can you only have a linearly ordered list. So in that sense, by just putting it below, you're already giving it much less attention, not just 2% less attention, but much less attention. So it's infeasible. So even if an object is marginally scored low on score, the attention it receives is much lower. So it is infeasible to achieve attention relevance parity within a single ranking. So what they're trying to achieve in this paper is about trying to look at a lot of rankings and try to adjust in a way that if consistently O1 and O5, if consistently O5 is only 2% less relevance than 2% less relevant than O1, you might sometimes put O5 at the top than O1, just because overall, over the course of many rankings, you want to ensure that the attention that O5 gets is only 2% less than O1, right? So you're trying to ensure some kind of relevance and attention parity. And how do you achieve it? So there's this paper called Equity of Attention, Amortizing Individual Fairness in Rankings in SIGIR 2018. What they try to do is, they say that attention relevance parity is infeasible to achieve within a single ranking, that we already saw, because you have maybe O1 which has a relevance of 0.97, and the next if you put it the top position, the next position can only get 50% of its attention, even if it has 95% of its relevance, right? So it's infeasible to achieve within a single ranking. You try and achieve it over a number of rankings over the same set of objects. So what do? You try to use an objective function which is unfairness over a number of rankings and objects, where you're trying to minimize the attention relevance disparity. You're trying to minimize the difference between attention and relevance. So while also maintaining that each ranking is close to its gold standard, you're trying to also ensure that the attention and relevance are evenly distributed. Okay. So just to summarize part 2, well, there are other kinds of fairness and rankings as well, but due to timing constraints, I'll just conclude now. So treatment fairness as a notion that is embedded in popular formulations for clustering and retrieval. So we looked at two kinds of fairness constructs. One is treatment fairness, one is impact fairness. Treatment fairness has already been taken care of in the vanilla framework of clustering as well as retrieval, whereas impact fairness is a notion that is not yet taken care of. So we need to deliver impact fairness by devising new algorithms. Impact fairness as a notion has not received much attention, and methods to address impact fairness in clustering and retrieval is about pre-processing methods, modified clustering objective, fairness conscious ranking methods for retrieval, etc. So that brings us to the end of this talk. If you have any questions or comments, please email me at deepaksp@acm.org. Thank you very much for your attention.